Welcome and thank you for being interested in the topic of tree extraction from mobile laser scanning data. First, I would like to ask the question, why trees? Well, trees are actually everywhere. They cover the countryside, large landscapes, but also large cities where they are planted in parks or along streets. Now, every time where nature meets human-built environment, we have to make sure that they don't interfere with each other so that problems may arise. That means that we have to keep an eye on those trees to avoid them from falling on people, on cars, on buildings, or just to grow somewhere where they shouldn't. We need some kind of tree register where every single tree is written into and we can look up its current status. To achieve that, we need a high level of detail with our information. That means spatial resolution must be high, and of course we want to observe changes, so we need high temporal resolution. In the end, to have that for each tree, we need the fitting sensor. The question is active or passive, and as we have to look through very thin branches and sometimes more or less occluded areas, we choose the active sensor, which is LiDAR in our case. The next question, from which platform do we observe? In the last years we had that shift from airborne acquisition to land-borne multi-sensor systems like mobile laser scanning. Of course, that can be combined with images, but for our application we only deal with laser scanning. So, we would like to present that concept on tree extraction, and to start we would like to compare some general assumptions. Often an assumption is introduced like trees grow strictly upwards, never downwards. But this is not true. Some trees grow strangely, especially older trees, so we would like to have our tree growing where it wants. Also, often it is considered that above the base, the footprint of the tree, there is the tree crown directly above it. This is not always true, so of course we have to assume that above our footprint there is a certain amount of points from the stem. But then our approach should deal with it like the crown can be everywhere where it likes, so we follow the stem up to the ground. The next assumption is the most important one and most often used. That is flat terrain. So flat terrain is mostly assumed that we can just extract our ground, but of course sometimes the terrain is more complicated and we need some kind of looking from downwards, from bottom to up, and to extract the first layer of ground that we meet there. More on that later. Now to our concept, which of course starts with the raw laser scanning data. Here we see an MLS point cloud, colored by intensity. The first step is to remove outliers. So sometimes if branches have moved or are too thin, the intensity is very low, so we filter by intensity. Then we might have duplicate points if we scanned some place twice or more. And of course there are statistical outliers that simply occur outside of some kind of point cloud that we would also like to remove. The basic data structure behind all that will be an octree in our case with an efficient binary addressing for easy and fast data capturing. The next thing we would have to think about is how to remove the ground, and we will do that by building pillars of voxel that grow from below and also examine the height of continuous pillars containing points. That means we start growing from the lowest level of voxels upwards, and then we meet the first points. That is our ground. Then we look in the next layer of voxels. If points are there, we continue growing, which builds us these kinds of voxel pillars. The high pillars are potential tree candidates, or at least high-rising objects. They are non-ground. The ground objects, on the other hand, will be low objects below a certain threshold, and of course the ground itself. After having removed the ground, we have something like those two point clouds. We see the ground cloud also contains low benches, and the non-ground cloud has all these high-rising objects, like trees, but also poles. So we of course use the high-rising objects, and from our growing approach we also have seed locations. So we know at this location on the ground there should be some object. And we can use these locations to start a region growing. So we grow to all the voxel neighbors of this area, and for every voxel we compute the centroid of its points inside. From centroid to centroid we can compute a distance, but not only the 3D distance, but also the 2D distance in the plane and the distance in Z. Having done that, we have a lot of information. We have these three distances, and we can grow and look how our clusters behave. Of course, they don't do what we expect, because sometimes they grow together. Some trees are really entangled into each other, and then we have large clusters. To dissect them, we use a graph cut approach. That means we look where in these segments is the border with the weakest combination, and there we cut it and derive two segments, and so on. To do that we need weights that say how strong or weak such a connection is. These weights can be distances again, but also other features like comparing normal vectors or primary components. This has to be examined further. In the last step, there is to be decided whether such an extracted object is an actual tree or something else. And these can be distinguished by their size and shape, because trees have a rather irregular shape, other human-built objects are more regular. This would be our workflow, and whilst doing that we also made some experiments on the data behavior. That is, having MLS point clouds, we removed the ground and just clustered them by Euclidean distance. Here in this cloud we see one characteristic of mobile laser scanning, that is that the point density grows weaker the farther we get away from the sensor. The second thing is we have our stems, all our data, only captured from one direction. We see that in these half circles that should be tree stems seen from above. So modeling will be complicated. Now if we zoom in, we see, yes, the clustering found some pole-like objects and especially trees, but as we see at these huge colored areas, many trees have grown together. Only some isolated trees, like here in the foreground, were extracted very well. The rest has to be dealt with by our normalized cut. In the end, we have to go on further research to find the features for region growing, for our weights for the normalized cut, and of course optimize that approach to deal with mobile laser scanning data, because that is our primary source. In the end, having those segments, we would like to use them to derive tree parameters for our register, to actually model the trees and to find changes in these trees. Like we see here, that is the same tree, 2 years apart. It seems to have tilted, and this is an indicator that its structure has weakened. Also, today in 2021, this tree doesn't exist anymore. So with this practical application, I would like to close this talk. I thank you for listening, and please feel free to contact me if there are any questions. Thank you.